Yes, so this is about the string model automata chemistry, and we found a need to formally define certain processes that have emerged in our experiments when things start getting complicated due to evolution. So string model itself, for those who don't know, it's an automata chemistry, which means that the strings in it are simple assembly language programs in a particular language defined for these experiments. The strings bind to one another probabilistically, and when they do bind, one starts executing its program. Which one starts executing depends on the location of the bind, and the string that starts to execute is called string 1, and the other is imaginatively called string 2. We originally called these the active and passive strings, but we changed the name because once evolution starts, that classification no longer really works. String model experiments are typically started with hand-designed strings that are designed to replicate. So the design is that the two strings bind, the two replicators bind, one executes and copies the other, and at the end of the reaction you have 3 replicator strings. However, there's a small probability of point mutation on the copy instruction, which means that you can end up with a mutated copied string. And with this very small point mutation, very complex behaviors evolve. So in these particular cases, this is spatial string model, and these are screenshots of the behavior of the system over a period of time up to something like 2 million execution time steps. And it gets very complicated and it gets very difficult to analyze. And I'll show here an example of how the complexity evolves. Here, the central string, this one in the middle, is string 1. And it shows 2 different reactions. And the top is a string 2 in a replication reaction. So at the beginning, string 1 binds to string 2. It starts to execute, and this line shows the execution path, the pointer, the path of the execution pointer in the string. So there's a program along here, and the execution pointer moves along until it gets to the copy loop, indicated in pink here. And then it copies, and what it copies is the string that it's bound to. Once it's copied the string, there's a little bit of tidying up phase, and then it terminates. And so the result is you start with 2 strings R, and you end up with 3 strings R. But parasites quickly evolve, and these parasites are simply shorter than the string replicator string. They've lost the copy loop, in fact, in this particular case. So if R binds to P and R binds as string 1, it executes and it copies P, and so you end up with R plus P, and then you start with R plus P and you end up with, actually that should say R plus P. Sorry, that's a typo. But in the other way round, if P is string 1 as the active string, it does not copy because it doesn't have the copy loop, and therefore we can class it as a parasite. It gets copied, but it doesn't copy in return. After a while, the replicators evolve defenses against this parasite. And so we see here, this is a new replicator that has evolved. It starts to execute. It gets to this point where it actually flips the execution pointer onto the other string. And so the other string starts to execute until it gets to the flip, and so it flips it back. It carries on, it gets to the copy loop, at which point it copies what it's bound to. But when it binds to a parasite, which does not have this defense in it, it flips its pointer, but the parasite doesn't have the blue region, and so it doesn't flip the pointer back, and so does not get copied. So that's a first defense. But the parasites rapidly evolve defenses to the defenses, and after a while, this is the kind of thing that's happening. You've got a replicator with lots of complicated flipping backwards and forwards and checking, and also the parasites are doing complicated defenses against these checks and so on. And it gets very complicated and very difficult to understand. So we need to work out what to do about that. we want to classify all these reactions in order to understand how parasites are evolving and what they're doing. So we need definitions of replicator and parasite that cope with all this complexity. But if we try and do something simple, like a replicator copies other strings, but actually its behavior depends on what the other string is. It may copy some and not others. And actually, with all this execution pointer flipping around, who's actually doing the copying? The copy code can be distributed between the two strings. And what if it copies the other string but destroys the other string in the process of copying? And there's lots of other things that can happen as well. And also we want to define a parasite, and maybe we would define it as a parasite does not copy other strings. Now this is a counterfactual property. We're saying something does not happen. And clearly if it doesn't happen, it's unobservable in the running environment because it hasn't happened. How do we cope with that? And again, parasitism depends on the other string. So there might be parasitic in some cases, but not others. And maybe this parasite does copy the other string, but destroys the original string in the process. And there's lots of these possibilities. And we observe lots of these possibilities after evolution has happened. So what we do is we take the strings out of the run environment and put them in a separate classification environment in order to study them and see what they're doing. And in this classification environment, the mutation probability is 0. So we can say what would happen in an ideal environment, not simply what happens because of chance mutation. And this environment also allows us to examine counterfactuals. We can test whether or not a particular thing can occur by trying to force it to occur and see whether it does. And this allows us to classify the reactions. But we still need to define what we mean by these different reactions. So I'm just going to introduce some very simple notation here. This is a reaction. We have two strings, A plus B, and the first one, A, is string 1, and the B is string 2. And afterwards, we've got A dash B dash, because they might be changed during the reaction. And then we also have a list of product strings, which itself might be empty. So let's look here, trying to define replication reactions. And so first of all, we'll start off just talking about a string 2 replication reaction, by which we mean it is string 2 that is copied. And we want to capture the notion there are more copies of string 2 after the reaction than before. It's not simply that the system copies string 2 because it might have destroyed the original string 2, and there are a variety of ways it can do this copying. So the simplest way is simply that you start off with string 1 plus string 2, and afterwards string 1 has copied string 2 to give you another copy of string 2. However, there are different ways that we can end up with replication. String 1 might copy string 2 but destroy the original string 2 but make 2 copies, so that there are now 2 B's afterwards, so in some sense it has been copied. Or string 1 might copy string 2 by changing string 2, overwriting itself with string 2, and then producing a string 2, a new string 2 as well. And again, we see these kind of complicated reactions happening. So we simply define a repl 2, which means string 2 has been replicated, as a reaction where the number of string 2s in the before state, which is actually 1, is strictly less than the number of string 2s in the after state, however that after state is composed of those string 2s. So this very clearly says, in a very general way, what we mean by replication of string 2. There are more of them after than before. And then we do something similar. We define a replication of string 1, because that can also happen as well in very peculiar ways, is simply a case where we have the reaction and there are more string 1s afterwards than there are before. There's one string 1 before and there are more afterwards. And then we say, now ignoring the fact that we're talking about string 1 and string 2, we simply say that string A replicates string B. So we define a replication reaction, A and B, is defined to be that B is replicated as string 2, or B is replicated as string 1. And so that means that afterwards, whichever happens, a REPL 2 or a REPL 1, there are more Bs afterwards than before, and so A has replicated B. And notice the fact that we have to change the order in this particular case, because it's REPL 1, it's B that's being replicated. And that change of order led to a lot of heartbreak when we were trying to get the definitions working in the first place. And then we can define the parasitic property using this replication property. We can explicitly capture the idea that R replicates P, but P does not replicate R. So we have a parasitic reaction in exactly defined as R replicates P and not P replicates R. And again, there are many ways for R to replicate P, as I showed earlier, but there are many ways for P not to replicate R, which all get captured by this not REPL P R. P might not replicate R because the string simply might not bind in the way that it could do that. It might bind and react but produce something other than R. It might bind and react and copy R but destroy the original R, and so on and so on. And all those complications are captured by that. So the definition is clear and it captures all the weird possibilities that can happen after evolution. There's a small wrinkle in these definitions because the way we do the analysis, we look at string 1 and string 2 separately, and so this clear, correct definition is not readily implementable. So we simply define something that is readily implementable in terms of parasitic on 2 and parasitic on 1, and then we do an equivalence proof to demonstrate that the definitions that we've implemented are equivalent to the definition that is clearly what we want the definition to be. And I call it an equivalence proof. That's a slightly grand term. It's actually a very simple little expansion of the more complicated definition, and a demonstration is the same as the other one. And then this allows us to analyze the results automatically. We can formulate these definitions into the analysis code, and we can use them to produce charts like this, or demonstrating how various parasites and replicators are evolving over time, and what these different regions are showing about how the parasites evolve. So just to conclude, what we need in these evolutionary systems is formal definitions, because the systems become so complex that we can't just use naive definitions and hope to capture all the weird edge cases. And in the paper, there are more definitions of unanticipated reaction types, not just parasites and hypercycles, but jumpers and various other weird things that we observed and then went and analyzed and formally defined. The definitions need to be intuitively clear so that we know what it is that we've defined. And this is especially so when there are lots of weird edge cases, and particularly when there are counterfactuals in the definitions. But also the definitions need to be readily implementable so that we can show and demonstrate that the code clearly does implement these intuitively clear definitions. And those can be in conflict. And so what we do is we produce 2 different definitions, one for each case, and then prove that they are equivalent at the end. So thank you very much.
Okay, thank you, Susan, for this nice talk. We have 5 more minutes for questions. Currently there's none, but I have one. So I think, I like this definition of the parasite, and I also liked how it can deal with all this complication. But in the longer run, and you already mentioned so that you also in the paper you also define hypercycles and then jumpers, and I guess I'm wondering how far can you go?
Yes. Yeah. So one of the things to notice is these are all post hoc definitions. So we did the definitions after we observed these peculiar reactions going on. But then we could analyze based on the log files that we had. All these definitions are either of single reactions or pairs of reactions at the moment, so they're reaction networks, and the pairs of reactions are when one string or the other string is the string one. But as more complex reactions occur, we have to then increase the complexity of our definitions. And in fact, we had a paper in A-Life last year where we were talking about how we can show that the system that we've got here is to some degree open-ended, because it is actually producing emergent properties which are being folded back into the way the system works. So, for example, macro mutations evolve in the system, and then the system exploits those macro mutations.
Oh, wow. Yeah, very interesting. Steen Rasmussen has a question in the Q&A. And he asks, could you give some examples of the more weird examples? What is a jumper? Okay, a jumper, I won't give the formal definition, but what actually happens, because this is spatial string mol, and so the new strings are put in somewhere in the neighborhood of the two interacting strings, which are next to one another. And what a jumper does is emulate movement by making a copy into a neighboring cell, but destroying the original copy. And so the apparent result is that string has moved. It's like a cellular automaton. There's no actual movement in the system, but it's an apparent movement because the string was there at the beginning, and there is now a copy of it there at the end, but there is no string there at the beginning. And so we call that a jumper. And that was something that was completely emergent. We were never anticipated that happening. And there's a kind of an emergent movement of the strings in the system. Okay, there's another question by Manuel Baltieri. He says, okay, Martin probably just asked the same anyway. How far do you think we can take this definition? As in, can we extrapolate some of these ideas beyond artificial chemistries, I guess?
I think in this particular case, what I'm trying to emphasize is that, one, we can't necessarily come up with all the definitions beforehand, and I'm actually in the open-ended evolution workshop later, I'm going to be talking about this a bit more. And the other is that we need a good definition of what the system is actually doing, given all its complexity. And I think the main thing that we learned from this is that you can't say a string is a replicator or a string is a parasite. You have to say a reaction network is a replication network, or a network is a parasitic network. And it's because it's not a property that exists in isolation, it's a property that only exists in context. And I think that's a lesson that probably goes beyond Aikens.
Okay, and maybe the last one, we still have time, by Steen also, why can't we see the question? The question sent by others. That's a meta question. I didn't know you can't see the questions sent by others. I don't know.
Sometimes you can, sometimes you can't. I have no idea why.
Okay, it's a bit of a pity.
Okay. No, it was changed. Sorry, there was some.
Okay, so there is maybe we can still do this last one. A question by Dragana: is the notion of symbionts covered within the model? The case when Parasite would become part of a replicator and get its code transmitted to following generations? Fascinating question. One of the things that we've noticed, and I did give a reference, that the main experiment is described in a paper that's just been accepted in Proceedings of the Royal Society Open Science. Excuse me, my alarm's just gone off. The parasites tend all to be derived from replicators. There isn't really a separate lineage of co-evolving parasites. Each parasite evolves from a replicator. So a replicator evolves a defense against a parasite, and then that replicator then evolves into a parasite that incorporates that defense. And so then the replicators then have to evolve further defenses against those new parasites. And that's where some of the complexities comes from. And that's what the other paper talks about, is this evolution of complexity due to having to evolve defenses
against parasites that include the code that was your previous evolution against the defense to the previous parasites. So it gets very complicated. Yeah.
Okay. Thank you, Susan, again. And